Okay, let's get to it. So we're going to continue with the theme today of duality and optimality. And the theme that we've seen is some very simple arguments lead to some pretty surprising and powerful tools. And the KKT conditions are no exception. They're very simple, and we're going to actually prove them today. We're going to prove both directions, that they're necessary and sufficient for optimality in a very broad context. But the proof is really, really simple. But what we get out of them is something that's quite powerful. So it's a very good tool to have in your toolbox. It's a good thing to be comfortable with. Before we start, are there any questions? Anything about stuff coming up? Do we have any announcements? Mattia or Nicole? No? Okay. So this is what we did last time. Last time we talked about duality in kind of its most general form, which was Lagrange duality. And we considered this minimization problem we've seen a bunch of times, very generic form. And we formed this quantity called the Lagrangian. The Lagrangian was formed by taking the criterion f and introducing what we call dual variables, ui and vj, one ui for each inequality constraint and one vj for each equality constraint. And we added the linear combination of ui times hi of x and vj times lj of x summed up over all the constraints. We added that to f. That formed the Lagrangian. It's a function of three variables, x, which was our original optimization variable, which we call the primal variable, and the dual variables u and v. And we have the constraint here that u has to be non-negative. It's an implicit constraint when we form this Lagrangian. The Lagrange dual function is given by minimizing this Lagrangian over all x, right? And we saw that at least in some cases that could be performed explicitly. It's not a constrained minimization over all feasible x to satisfy the constraints or anything like that. It's just an unconstrained minimization over all x. So the dual problem subsequently, right, is to take this dual function we formed g, which is given by minimizing the Lagrangian, and to maximize it, subject to the implicit constraint, like we said, that u has to be non-negative in every component. This is called the dual problem, and we saw just by construction that this function guv, it lower bounds f of x whenever x is primal feasible and u and v are dual feasible, which means that u is non-negative in each component. So that means that, in particular, GUV lower bounds the primal optimal criterion value, f star, right? Because it's smaller than or equal to f of x for all feasible x. So it's going to be smaller than or equal to f star. And when we maximize overall u and v, we still get the same relationship. That's called weak duality. So if we were to solve this problem and write down its optimal value, the dual optimal value g star, we have by construction that f star is always bigger than or equal to g star. So it always forms a lower bound on the primal criterion value. That was one kind of fundamental property of the dual problem. Another one was that the dual problem is always convex. So even if we started off with a primal problem that was non-convex, we would always end up with a concave maximization in the dual, because g is always concave. We saw that from a very simple argument that just came from the fact that it was could be written as a pointwise maximum of things. So that means that in principle, if we could form the dual problem, then we'd have a convex optimization problem, and that would be one that would be tractable, whether or not the primal was convex or not. The last property we saw was to do with strong duality, which is a condition. We're trying to find a sufficient condition for when we have f star equals g star. We actually have the lower bound we construct from the dual problem equal the primal optimal value exactly. So there's no gap. This inequality in weak duality is tight. That's called strong duality. And we saw this general condition called Slater's condition is sufficient for strong duality. So if Slater's condition holds, we know we have strong duality. And Slater's condition just says that the primal problem has to be convex, and there has to be an x that's strictly feasible, which means that we can strictly satisfy all the inequality constraints, and it still satisfies the equality constraints. There's an even weaker version of Slater's condition we saw, which is that we only need to have strict inequality for the non-affine inequality constraints. It's a very weak condition. It would be pretty unusual that you wrote down a problem that was convex for which Slater's condition didn't hold. Right? If a point wasn't strictly feasible, then that would be a pretty peculiar problem. That if there didn't exist a strictly feasible point, it'd be a pretty peculiar problem that you're writing down. Okay. Is there any questions about duality? So we learned last time. Okay, so today we're going to talk about the KKT conditions, which in some courses or in some textbooks are taught before duality, and in some courses or textbooks are taught after duality. I like to think of them as following from duality. So we're going to actually prove the KKT conditions as necessary and sufficient for optimality from basic duality concepts. We're going to go through a bunch of examples, and then we're going to talk about some common things that you might encounter in stat and ML problems, like constrained and Lagrange forms of penalties or of regularization, and some issues of uniqueness, some surprising things you can do with the KKT conditions. So the KKT conditions, again, we're going to be in this general problem form, right, where we have criterion F, inequality constraints HI, and equality constraints LJ. At this point, again, for the sake of generality, we're not going to assume that this problem is convex, so of course that's going to be kind of of special interest to us, and we'll kind of see when we need to make that assumption in a second. But for any problem, you could write down, there's an associated set of conditions called the KKT conditions. They stand for Karush-Kuhn and Tucker conditions. So 3 people. And there are a set of 4 conditions. The first condition is called the stationarity condition, which says that the point x, well, I won't say exactly how to interpret this yet. Let's just read it off, and we'll interpret it in a few slides. It says that 0 has to be in the subgradient of f of x plus the sum of ui times the subgradient of each hi of x plus the sum of vj times the subgradient of each lj of x. Okay, so that's like saying that if we wrote down the Lagrangian, right, which was f of x plus the sum of ui hi of x plus the sum of vj lj of x, and we took the subgradient with respect to x, treating u and v as fixed, then we're saying that there has to be 0 subgradient of the Lagrangian at x. The second condition is called complementary slackness, which says that ui times hi of x has to be 0 for all I. So if you look at this inequality constraint, it's saying either the inequality constraint has to be tight, which means that hi of x is 0, or ui has to be itself 0. You can't have both ui being bigger than 0 and hi of x being strictly less than 0. That would violate the complementary slackness condition. The last 2 sets of conditions are just feasibility conditions. So there's a primal feasibility condition which says that x has to satisfy all of these inequality and equality constraints, and the dual feasibility condition, right, is very simple. It's just that ui is bigger than or equal to 0 for all I. So we say that a triplet x, u, and v, or a pair, primal x, dual uv, satisfy the KKT conditions if the following 4 conditions hold with those 3 variables. Okay, so it's a condition on x, u, and v. So these conditions we're going to see are very, very closely related to optimality, and the arguments for that are very simple. Optimality of x with respect to its own problem, the primal problem, and u and v with respect to their own problem, the dual problem. And we're going to prove each direction. So let's go with the necessity direction first, which means that if we have primal and dual solutions, x star and u star v star, and there's 0 duality gap, then we're going to prove the KKT conditions must hold. Okay? So we're in a situation where we assume that we've solved the primal and the dual, and we have 0 duality gap, which means that we have strong duality. F star is equal to G star. Remember, when would that hold? That holds, for example, if the primal was convex and we had strict feasibility of its constraint set by Slater's condition. So let's just start off with the assumption that we've written down, which is that f star, which is equal to g star. That's our assumption, right? That we've solved the primal and the dual, and we get strong duality. In other words, because we're assuming that x star and u star v star are solutions, this is what we have by assumption. Okay, but what is GUV for any fixed u and v? Doesn't matter that it's u star and v star. For any u and v, including u star and v star, the definition of G is to minimize the Lagrangian over all x, right? Which is f of x plus the sum of ui star hi of x plus the sum of vj star lj of x. Okay. And this minimum over all x, right, is in particular going to be smaller than or equal to what happens if we evaluate this function, the Lagrangian, at x star, right? It's just a trivial property that if I take the minimum over all x, it has to be less than or equal to the value of this function for some x, in particular for x star, or for any x, in particular for x star, so I'll just plop that in. And now, since x star is feasible, right, what do we know? We know this is less than or equal to 0. X star must be feasible since it's a solution, right? There's no doubt about that. So it must satisfy the constraints. This is equal to 0. And ui is bigger than or equal to 0 because it's a dual solution, so of course it must be feasible too. So this whole term here is less than or equal to 0, which means that this is less than or equal to f of x star. Okay, so what have we argued? Let's just look back at it. We've argued that f of x star is equal to the dual optimal value, g of u star v star, but in turn we can bound that by f of x star. Just by definition of the Lagrange dual function, and then a simple bound that said that the minimum over all x has to be the value of the function when I plug in x star. So what does that mean? That means that all of these inequalities must be equalities. Right? Because I have equality between these two. So this cascade of inequalities, then all of these must be equalities. So let's just label these one by one, and let's see what they imply. So the fact that I have that f of x star plus, the sum of the dual variables times hi of x star plus dual variables times lj of x star is equal to the minimum of that over all x. So the fact that this minimum is equal to what happens when I plug in x star, implies that x star minimizes the Lagrangian over x. Right? And in particular, just so you're not confused, equality in 1, right, which we know must hold, implies that x star minimizes the Lagrangian over all x. It's another way of writing that. Right? We know that a point achieving the minimum of a function is equivalent to 0 being in the subgradient of that function evaluated at that point. Right? That's subgradient optimality condition that we know. So that's true if and only if 0 is in the subgradient. I'm going to write it like this: with respect to x of L of x star u star v star. Just to be clear that we're considering this function, Lagrangian, as a function of x alone, with u star and v star fixed. Right, which is another way of just explaining that out, says that we have to have the following hold. That look familiar? That's just the stationarity condition. So equality in 1 implies the stationarity condition. Okay? So now we've proved part of the KKT conditions. We've proved that if X star and U star V star are primal and dual optimal and we have strong duality, then the stationarity condition must hold. We also want to prove that the other conditions must hold too. So let's look at this inequality here too, which we know must be an equality. So equality in 2 implies what? It implies that, well, all of this must be 0, right? This term is already 0. That means that this sum must be exactly 0. Not less than or equal to 0, but we know now exactly 0. But it's the sum of quantities that all have the same sign, right? So it implies that must be 0. But this implies, because each of these have the same sign, this is bigger than or equal to 0, and that's less than or equal to 0. That each term must be 0. Right? And that's just exactly complementary slackness. So now we've knocked out 2 of the KKT conditions. The other 2 are trivial, right? So primal and dual feasibility are going to hold automatically. Because if we have solutions, of course they must be feasible. So I'll just put a check mark there. So now we've just showed that if we have solutions with a strong duality gap, with strong duality, which means 0 duality gap, then the KKT conditions must hold. Questions about that? Nothing complicated in these arguments, right? They're very basic, but we're going to see the KKT conditions are a very useful thing to know. Okay, let's apply, and let's do the other direction now. That was necessity. Let's do sufficiency. Right, which we're trying to show now that if we have a triplet that satisfies the KKT conditions, then we want to prove that the corresponding X star is primal optimal and the corresponding U star and V star are dual optimal. Which means the KKT conditions are sufficient for optimality, the other direction. Okay, well, let's write down the Lagrange dual function, which is the minimum over all x of the Lagrangian, right? Lx U star V star. Well, by the stationarity condition, right, because you know that subgradient optimality goes both ways, the stationarity condition tells us that X star achieves the minimum here, because 0 is in the subgradient of this with respect to X when we plug in X star. That's just stationarity. So we know this is exactly equal to L of X star U star V star by stationarity. The first of the 4 KKT conditions. Let's just write out what this is. Okay, so by feasibility, this is equal to 0 by primal feasibility, right? And this one is equal to 0 by complementary slackness. right? Because each term is equal to 0 by complementary slackness. So what do we get? This is just equal to f of x star. So if I tell you that I have g of u star v star, where u star and v star are dual feasible, is equal to f of x star, where x star is primal feasible, then this implies, right, that x star is primal optimal and u star and v star are dual optimal. Because in other words, we've just shown that the duality gap is 0 between these two. And from what we know last time when we studied duality, right, we saw that if the duality gap is 0, then that implies that we must have the primal and dual solutions. Yeah? Stationarity condition implies that for this function, so if you look back at the stationarity condition, it implies that for this function, the Lagrangian, its minimum over x is achieved at x star. So the assumption here is that x star, u star, and v star satisfy the KKT conditions. So if these satisfy the KKT conditions, then the following steps hold. So the stationarity condition, right, just think of this as a function of x alone. This is saying that the subgradient of that function over subgradient of that function when evaluated at x star is 0, has 0 in it, in the subdifferential, which means that x star achieves the minimum here. Yeah?
What happens if strong gradient doesn't hold?
It's a good question. So, yeah, we'll get that to next slide. We'll kind of put it together. Okay. Right. So just to be clear, this was necessity, which means that we are assuming if x star is primal optimal and u star v star are dual optimal, then the following stuff holds. Okay. So what did we learn? The KKT conditions are always sufficient. So any problem you write down, convex or not, they are always sufficient. Which means that if you satisfy the KKT conditions, you have a primal solution and a dual solution. Now there's a big caveat there, because people see this and they think, I can minimize any problem I want with the KKT conditions. What's the caveat? Let's go back to the KKT conditions. So stationarity is the one that's difficult to satisfy here for non-convex problems. Okay, if my primal problem is convex, and all my constraint functions are differentiable, and my criterion is differentiable, right? So if f, hi, and lj are convex and differentiable, then the stationarity condition is the same as saying that 0 is equal to the gradient of f of x star plus the sum of ui star, the gradient of hi of x star plus the sum of vj star times the gradient of lj of x star, right? Because for convex differentiable functions, their subgradients are just their gradients. There's only one subgradient, and that's the gradient. So you look at a smooth convex problem, and you'd say, stationarity condition is just taking the Lagrangian, forming it, taking the derivative or the gradient of all the functions, setting that equal to 0 and solving. Making sure that you have x star and uv star that make this true. For non-convex problems, right? This is not the same as the stationarity condition. Right? So for f, hi, or Lj not convex, this is not true. And people make this mistake a lot, so it's important just to be clear about it. The stationarity condition says that if we take a subgradient, of these functions, then we must make that subgradient equal to 0. If we have non-convex functions that are still differentiable, remember, we saw this already, subgradients and gradients are not the same thing. So you can't just write down the derivatives of your functions and set equal to 0 and solve. So the big caveat is that, yes, they're always sufficient, which means that if you could satisfy the KKT conditions, you have a solution, primal and dual solutions, but you have to actually satisfy the stationarity condition. You can't write down gradients, even if you have smooth functions in the non-convex realm. You have to actually think about subgradients, which are much, much harder to calculate, right? Because non-convex functions need not have subgradients at all. Okay, so that was just something we saw. Always sufficient. They're necessary under strong duality. Okay, so putting it together, we can say that if we have a problem with strong duality, for example, if we had a convex problem under which Slater's condition held, then the KKT conditions are necessary and sufficient for optimality. And that's the most common application of the KKT conditions is in this case. Right, on a convex problem, we check that Slater's condition holds, which means we know that strong duality must hold. And then the KKT conditions completely characterize the solution. They're necessary and sufficient for optimality. Okay? In one direction, just to repeat, they're always sufficient. So that means they're actually quite powerful. They're always sufficient, even outside of strong duality, even outside of convexity, etc. In the other direction, we proved that they only held under strong duality. And so to go back to your question, in general, without strong duality, the KKT conditions don't characterize optimality. If there's a duality gap, then you can see immediately from our arguments that the same arguments won't go through. We needed the duality gap to be 0 in order to basically leverage the KKT conditions. Yeah?
Even if the function is non-convex, isn't 0 being a subdifferential at a point x, doesn't that mean it's optimal?
Yeah, we're not saying that 0 has to be the subgradient of f of x star, right? Of f. We're forming something else. So, okay, you're asking a good question, and I think we'll get to that in a second, which is, could we have gotten this from subgradient optimality alone? And the answer is yes. But it's a lot harder to do that. I think it'll become clear in a second what I mean by that. Other questions? Okay, so here's just a bit of interesting history. If you look at old enough textbooks, like, for example, the Rockefeller textbook, then these will be known as the Kuhn-Tucker conditions. Because Kuhn and Tucker, they're two very famous convex analysts. They published these conditions in 1951. And so for a long time, I think until, Javier will know better than I do, I think until at least the 70s or 80s, it was just known as the Kuhn-Tucker conditions. And then people found out later on that a master's student, Karush, had these in his master's thesis in 1939, so a lot earlier. So to give him credit, now the community has appended his name to the front, so it's known as the KKT conditions, Karush-Kuhn-Tucker. So for those of you guys who are master's students, you now have a goal to set for your master's thesis. And for those of you guys who are PhD students, you know what you have to surpass with your thesis. Okay, so for unconstrained problem, the KKT conditions are nothing more than just a subgradient optimality condition, right? If we look back and we have no constraints whatsoever, so that means that M is 0 and R is 0, so we have no inequality or equality constraints, then stationarity, right, there are no dual variables here, reduces just to 0 being the subgradient of f of x. We already know that's necessary and sufficient for f being minimized at x. All of these conditions are vacuous. Right? They don't mean anything because we have no constraints. So for unconstrained problems, KKT conditions are the same as subgradient optimality. In general, right, if I wanted to, I could have written down I could have written down C as the set of all x for which hi of x is less than or equal to 0 for all I, and Lj of x is equal to 0 for all j. And I could have written my problem in the following form: minimize f of x plus the indicator function of x being in C. Right? We've seen this trick before. This will be infinity when x is not feasible, and it'll be 0 when x is feasible, so it's equivalent to minimizing f subject to the constraints. Then I could have just said, okay, let's apply subgradient optimality to this function. X is optimal if and only if I take a subgradient in this function at x and it contains 0. That's actually perfectly legitimate. That is another way to derive the KKT conditions. So if you want to see how that's done, you can look at Rockefeller. That's one way he does it in his textbook. It's a lot harder to manage, right? This involves the normal cones of our constraint functions. We've already seen that before. Right? Indicators and have subgradients that look like normal cones. It's a lot harder to manage a condition like this than it is to manage the KKT conditions. So while this is just as general, the KKT conditions are easier to deal with. So we tend to think of them for constraint optimization problems rather than just subgradient optimality. Okay, let's do a few examples. I think it'll help make the KKT conditions a little more concrete than they are now. The first one we'll do is a quadratic with equality constraints. So we already know how to minimize a quadratic unconstrained, right? That's in some sense the simplest optimization problem we could write down. Let's do a quadratic with inequality constraints now. So suppose we're going to minimize the quadratic form, 1/2 x transpose qx plus c transpose x, where q is positive semi-definite so that this is convex. Subject to the equality constraint that a times x has to be equal to 0 for some matrix A. So we're going to see this as being important when we talk about Newton's method, subject to equality constraints. Okay, in Newton's method, we're going to iteratively form quadratic approximations of our function. We're going to minimize those, similar to what we did with gradient descent. But in Newton's method, we're going to actually use the Hessian for that quadratic approximation. When we have equality constraints, the inner problems are going to be taking quadratic approximations where we preserve the equality constraint in this sense. So this is going to be kind of like our fundamental computational unit for equality constrained Newton. We'll see that in a couple lectures, 3 lectures or so. So let's see if we can write down the KKT conditions for this problem. Right, so let's just go through them one by one. What does complementary slackness say? Complementary slackness says that if I take the Lagrangian, let's write down the Lagrangian first. It's only a function of x and v. We have no u because there's no inequality constraints, right? Which is just the criterion plus v transpose ax. It's Lagrangian. If we take the derivative of this, the gradient of this with respect to x, then we get 0. Why is it a gradient, not a subgradient? It's because all of these functions are convex and differentiable. So stationarity says that the gradient of this is 0. What's the gradient of this? Right? It's just q times x plus c plus a transpose v equals 0. Okay? Complementary slackness empty. There's no condition, right? Because there are no inequality constraints here. Complementary slackness is a condition on the inequality constraints either having to be tight or the corresponding dual variable having to be 0. But there are no inequality constraints. Primal feasibility says that ax has to be equal to 0, and dual feasibility is again vacuous because v here is not constrained and we don't have a u for the inequality constraints. So the KKT conditions reduced to these two set of conditions. If we can find an x and a v that satisfies these two conditions, then we have minimized this problem. So let's put them together. We can actually write them in a more succinct form by writing them as follows. See if I did this correctly. Okay, so the first equation reads qx plus A transpose V equals minus C. That's just the complementary slackness condition. The second block of equations here reads AX plus 0 times V equals 0. So that's just AX equals 0. So now all we have to do is solve one single linear system, and we get the solution to this equality constrained quadratic. Okay, it's a bigger linear system than we had to solve if we only wanted to find the minimizer of the quadratic unconstrained. Right? In that case, we would write down qx plus c equals 0, the gradient equals 0, and we'd solve that system, qx equals minus c. It's a bigger linear system now that we have linear constraints, but it's still just a single linear system. Sometimes this is called the KKT matrix, by the way. It's just a terminology I've heard applied to equality constrained quadratics because it encapsulates the KKT conditions. All right. Let's do another example. This one a little more sophisticated. Another convex problem, which is sometimes called, I guess, communication optimization or water filling. You'll see why it's called water filling, because essentially we can reduce it to a problem that's akin to a water filling problem. So the problem is to minimize over all x the following criterion. Minus log of alpha I plus xi. Alpha I here is a constant. These are given to us. Subject to x lying in the probability simplex. So x, think of it as a vector of weights. They're all non-negative, and they sum to 1. Okay, so if we think of this as, we think of log of alpha I plus xi as something like the communication rate of channel I, then this problem is to minimize the communication rate, the negative communication rate across the sum of the channels, or maximize the communication rate across all of the channels. And these are allocations across all of the channels. That's why we have this kind of probability simplex constraint here on x. Okay, so this problem comes up, I suppose, sometimes in information theory. This type of problem, maybe not this one exactly. But let's write down as KKT conditions. Okay, so let's go through them one by one like we did last time. Stationarity just says that if we form the Lagrangian, we take its, in this case, again, it's a gradient with respect to x because all of these functions are convex and smooth. Then we have to have that equal to 0. So the Lagrangian, right, is, let's write it down up here. It's just the minus sum of logs plus, it's actually going to be minus u transpose x plus v times 1 transpose x minus 1. Okay, so stationarity, we're going to get by differentiating this with respect to x. So we get minus the sum of 1 over alpha I plus xi. Oh, let's differentiate each component. That's probably easier. Let's differentiate with respect to the ith component, say, xi. So we get minus 1 over alpha I plus xi minus ui plus just v equals 0. That's the stationarity condition. This must hold for all I. Complementary slackness says, right, that the sum of the ui times xi has to be equal to 0 for all I. And then there's, of course, primal and dual feasibility. So these are the KKT conditions. If we found x, u, and v to satisfy this, we would have solved this problem. So let's go ahead and first eliminate u from the KKT conditions. We can reduce them to a, this was, by the way, complementary slackness. These were our feasibility conditions. Let's eliminate u and come up with an equivalent set of conditions, right, which we can see that we can do, say, by solving for u here. Let's first solve for u. So stationarity says that ui must be equal to v minus 1 over alpha I plus xi. So then we can plug that in and get a different complementary slackness condition, which looks like the following: xi times v minus 1 over alpha I plus xi equals 0. It's our new complementary slackness condition. And now let's combine dual feasibility and stationarity to say that we have to have 1 over alpha I plus xi being less than or equal to v. Okay, so now we've simplified the KKT conditions a bit. Okay, and now we're going to argue directly from the KKT conditions that essentially xi has to take a certain form as a function of v. So let's consider two cases. Let's first consider the case when v is strictly less than 1 over alpha I. So let's try to read off from the KKT conditions what we must have for x. So let's suppose that vi was strictly less than 1 over alpha I, and we chose x to be bigger than 0, something bigger than 0. All right, so let's suppose first we chose xi to be equal to 0. Is that going to work? Let's look at these set of equations here. Well, first of all, that's not going to work, right? Because this is telling us that if xi were 0, that we have to have v bigger than or equal to 1 over alpha I, and we are assuming in this case that it's less than 1 over alpha I, so it can't be equal to 0 because it would violate the transformed stationarity condition. And if xi is not equal to 0, then by complementary slackness, this term has to be equal to 0, right? Because their product has to be 0. So we get that solving for xi, we have to have xi equal to 1 over v minus alpha I. That just comes from solving v equals 1 over alpha I plus xi. Okay, and if we go back and read off kind of a complementary condition, which is, let's suppose that v is bigger than or equal to 1 over alpha I, then you can see that we can't have xi strictly bigger than 0. Right? Because if xi was strictly bigger than 0, then this would not be 0, and this wouldn't be 0 either, because this would just get smaller, and this is already bigger than or equal to 1 over alpha I. So we have to have xi equals 0. Right? Because xi has to be non-negative in every component. So straight from the KKT conditions, we've essentially solved out for x now. We've gotten rid of u, we've gotten rid of x. The KKT conditions are a problem that only involve v. Right, so let's write out what xi is. We've said that it's equal to 1 over v minus alpha I, or 0, if v is less than 1 over alpha I, and 0 if v is bigger than or equal to alpha I. Another way of writing that is this just the maximum of 0 and 1 over v minus alpha I. You can see that that encapsulates both those two cases exactly. Okay, so now the KKT condition is reduced entirely to just this single feasibility check. 1 transpose x has to be equal to 1. Okay, because by our choice of x and v, these two are always satisfied. This one's always satisfied. All that's left to check the KKT conditions are to check that x sums to 1. So the KKT condition is reduced to the sum of xi being equal to 1, which I'll write as like this. And this is now solving for a single number v, right? We've reduced the KKT conditions, which are how we had an n-dimensional optimization problem, to solving a single equation in one number, which is v. This is actually a piecewise linear equation, right? If you look at it, each of these functions is piecewise linear. It's a sum of piecewise linear functions, so it's piecewise linear, and it's actually not hard to solve. You can do it in the time equal to the number of pieces here, which is n. And the reason it's called the water filling problem is because you can think of, for example, alpha I as the height, if you look back at this picture, of a bunch of different units from the floor. So we lay down n units, and we kind of dump water in, and the level of water at each unit is either, it can't go below the ground, so it's 0, it's at least 0, or it's the water level, which we keep track of as 1 over v, piecewise linear equation, and 1 over v, above the floor, the height of that unit, which is alpha I. Okay, and we essentially increase the level of the water, 1 over v, until the total content of water is 1. That's why it's called water filling. The lesson to see here is maybe not necessarily that it reduces to this in particular, it's just that the KKT conditions subject to manipulation can turn a much more complicated problem, right, this problem, into a fairly simple one, which involves a single variable. Once we have the solution to that, we can back solve for x, which is what we cared about in the first place. Questions about that?
The code seems to be very problem specific. Is there a general way to increase KKT conditions to solve general problems without looking at the cost function specifically?
Well, you can guess the answer is no, because if there was, then there would be nothing difficult about optimization, right? If there was a general way to write down the KKT conditions for arbitrary problems and kind of get something simple, then that would make everything easy. So maybe that's unfortunate, maybe that's fortunate, depending on your enjoyment of optimization. But there are kind of classes of problems that we can analyze, and that's something that we'll see over and over again. So, quadratics are very easy to deal with, quadratics with constraints. For example, penalties are quite easy to deal with. We'll talk about that later. Norm penalties, like the L1 norm, L infinity norm. So, yeah, classes of problems we can solve pretty easily, but in general, no. Other questions? Yeah.
Just curious, using KKT, how could researchers find solutions for classic problems or several problems for which nobody found answers before? Or is it just at OB?
Have people found so certainly I would say that, one could solve this problem, right? So we haven't quite learned how to solve this problem yet. Actually, no, we have, right? Because you could look up you could Google projection onto the simplex, find an algorithm for that, and you could run projected gradient descent here. So this problem is not one you couldn't solve, but it's a lot easier if you use the KKT conditions.
Is that like closed form solution? Closed form solution doesn't necessarily mean we have
We don't have a closed form solution here as well. I mean, this in general is not of a closed form solution. Because it depends, right? The value of v that makes this true is not closed form. I mean, it's like a function of n if statements, because it's like a piecewise linear function with n segments. But it's a lot easier to solve this than to run projected gradient on this. So in general, I'd say the KKT conditions, they do two things. They either make problems a lot more tractable, or what we'll see later in the lecture, they give us an understanding of problems we couldn't understand before, because they completely characterize optimality. So even if we can't solve a problem, we can still understand properties of its solutions by looking at the KKT conditions. And that can be very helpful for statistical purposes, say. All good questions. Other questions? Okay, let's take a quick break, and then we'll come back and do a few more stat ML examples. Okay, we're going to go through a few examples here, and these are now more kind of statistics and machine learning focused. The first example we're going to go through is the SVM problem, the KKT conditions for that. We've gone through SVMs a few times, right? A few times earlier in the course, and then we talked about the dual of the SVM problem. So I'm going to try to go through this pretty quickly. But you'll see that what we get out of it is not... So the dual problem we derived was another way of solving it. We could solve the dual instead of the primal. The KKT conditions, unlike the water filling example, they're not going to reduce to something very simple to solve. So it doesn't give us a better way of solving SVMs. But it lends to some understanding of SVMs that we may not have had before. And the plan is currently, at the end of the semester, to come back to SVMs and kind of problems where we use sparsity penalties and talk about screening rules, which are pretty popular nowadays. And we're going to see that the stuff we learned from the KKT conditions is really important then. So we'll revisit this at the end of the semester when we talk about screening rules. So let's go through the SVM problem, right? Just write down the criterion. As we've seen several times, we have points yi, which are -1 or 1, xi, which are real-valued predictors, and an RP, with n of them. And we form a triplet of variables, beta, which kind of determines the hyperplane that we're going to use, the separating hyperplane we're going to use for classification. Beta naught is an intercept term in that hyperplane, and these psi variables are slack variables. We're going to not require perfect separation, but we're going to penalize kind of points lying on the wrong side of the hyperplane, according to these psi's. So the criterion is to minimize the margin of the hyperplane, which ends up being the norm of beta squared, plus some penalty on having points on the wrong side of the margin, wrong side of the hyperplane. That's this psi I variable. And C is a tuning parameter. It's the strength of that penalty, subject to usual constraints, which is that each of these have to be non-negative, and we have to have the classification rule, which takes yi, which is just -1 or 1, and multiplies it by the sign of, or multiplies it by xi transpose beta plus beta naught, and says that it has to be no farther from 1 than psi I. Okay. Let's write down the stationarity condition now. Try to do it without. So the last two times we wrote down the Lagrangian explicitly. Let's try to just do it by reading off of the problem. It's good practice if we can do it without forming the Lagrangian. So we're going to take all of this, form a Lagrangian kind of on the fly, differentiate it with respect to beta, beta naught, and psi. So let's first differentiate with respect to beta, and let's put down a set of dual variables. I think I called them in the notes wi here and vi here. Okay, these have to both be non-negative. So with respect to beta, what does stationarity say? It says that, well, this just gives us beta, right? Plus any combinations we take here with vi and psi don't involve beta, so they don't matter. We take the gradient. Any combinations we take here with wi and yi this is not transpose, it's just times. Yi is real valued. Right? This just is going to reduce to the sum of wi, yi times xi, because as a function of beta, it's just a single linear function of beta. And it's this linear function transpose beta. So when we take its gradient, that's what we get. So this must equal 0. Actually, I did something a little bit wrong here, which is that I should have subtracted this over to the other side, because I should have this constraint less than or equal to 0, which means this should have been a minus sign. So that's the stationarity condition with respect to beta. Again, we kind of did it on the fly. And I'm going to rearrange it to say that beta has to be equal to the sum of wi, yi, xi. That's actually very interesting. We'll come back to that condition in a second. How about with respect to psi? So what happens if I differentiate this with respect to psi? Right, this term goes away. I get c times 1, the 1's vector, because this is just c times 1 transpose psi. Here I get minus v, because the Lagrangian would have had a term look like minus v transpose psi I. And here I get, this is going to look like minus w. That's it, because I'm going to multiply, I'm going to write this 1 minus psi I minus this stuff less than or equal to 0, multiply that by wi, so the gradient looks like that, equal to 0. Okay, so again, I'm going to rearrange that and just say that that means that c times 1 minus, the 1 vector minus v has to be equal to w. Now let's do with respect to beta naught. This one's very simple. There's only one appearance of beta naught. It's here, right? And it just tells me that minus the sum of wi, yi has to be equal to 0. If I bring this over to that side and multiply by wi and take the gradient with respect to the derivative with respect to beta naught. And so the minus doesn't matter. So those are our stationarity conditions we just derived with respect to all of our primal variables, right? We just split it up into blocks over each block of primal variables because it's more convenient to write it that way. Complementary slackness says that vi times psi I has to be equal to 0. This is complementary slackness. And also that wi times 1 minus psi I minus yi xi transpose beta plus beta naught equals 0. And dual feasibility is here, and primal feasibility is written down up there, so I'm not going to rewrite them. So these are the KKT conditions for the SVM problem. One thing that's very interesting, this is the first time we have seen this so far, but it's a general principle that we'll get to at the end of today and next time, is that, look, w is a dual variable here, right? So these w and v, by the way, just so that we're clear, are the same dual variables that we would have gotten if we formed the dual, right? Because we would have done it the same way. We introduce them with their constraints. We minimize the Lagrangian, get the Lagrange dual function. Then that forms the dual. These are the same u and v here. So, of course, if we satisfy the KKT conditions, then beta naught, and psi would be primal optimal, and wi and vi would be dual optimal. So w would be, for example, w would be the solutions of the dual. This is telling us that had we satisfied, had we solved the dual problem, and we took w and we summed it up, wi, y, xi, that would have given us the vector beta that determines the hyperplane. So it's the first instance we've seen where the primal solution is given by a dual solution. First time we've seen this relationship. So again, this is really the reason I think we care about duality most of all, not because the criterion values are equal. That doesn't mean much. It's because under some conditions, and we'll return those at the end of the lecture, and we'll go through that in detail next time, we can actually get primal solutions from dual solutions. So this is our kind of first example of that. Okay. What else did we learn from the KKT conditions? That's one thing we learned, that had we solved the dual, we could have gotten the primal solution. Well, we also learned that the primal solution only really depends on the values of I, so the points, right, because I and x is the points, for which wi is non-zero. If wi was 0, then the primal solution beta, which determines the hyperplane, doesn't depend on the pair xi, y at all, because they don't appear in this sum. So those are called non-support points. And the support points are the values of I for which wi is bigger than 0. So the support points that we learned so these are I such that wi is bigger than 0. These completely determine beta, the primal solution for the hyperplane. Okay, we can actually know even a little bit more than that. Let's suppose we had a support point. So we had wi that was non-zero, so it's strictly bigger than 0. What do we know here? Let's suppose that we had a support point and it so happened that psi I was equal to 0. Okay, so if that's the case, right, then we know that by complementary slackness, that vi has to be bigger than vi has to be or can be bigger than 0, right? Which means that we can have it being the case that according to this equation, the w could lie anywhere between 0 and c, right? Because wi is equal to c minus vi. Because psi is equal to 0, vi is allowed to be bigger than 0. So we could have w being, for example, c over 2. That would be a perfectly legitimate choice according to the KKT conditions. If psi I is not equal to 0 for a support point, then what does that tell us here? It tells us that actually, well, vi has to be equal to 0 to satisfy complementary slackness. And now if we go back up to this condition, it tells us that wi is going to be equal to c. So we've just kind of learned something about the support points, which is that the support points for which psi I equals 0, which, by the way, the meaning of that is that it lies on the edge of the margin, right? If we go to this picture, for example, these two green points lie on the edge of the margin. They are support points for which psi I is equal to 0. Then the weight they contribute in the overall determination of the margin can be anywhere between 0 and c. But if I have a support point that lies on the wrong side of the margin, like any of these points, for example, then they have maximal weight. They contribute exactly c in the formulation of the primal solution. So we're going to come back to the SVM problem in detail at the end, and we're going to learn that there's a strategy for what's called support point screening. So that means that before we even solve the SVM problem, we're going to use the KKT conditions, exactly what we wrote down here, this logic, and some trickery to show that we can actually just throw out some data points ahead of time, because we know they're not going to be support points at the solution. So you give me a huge data set, say 100 million points, I might do some kind of cheap operations to determine that, well, if I were to solve the problem, then wi would be 0 at that solution, so it wouldn't actually figure in at all in the formulation of the margin, so I don't have to even consider that data point at all when I solve my SVM. That's called a screening rule. We're going to get to that as an advanced topic. And this logic is going to be very important for that. Any questions about that? Okay. Here's another topic that I think is one that we run into all the time in stat and ML, and that's constrained versus Lagrange form. Right? We have our favorite problem. We have our favorite loss function f and our favorite, say, regularizer h. And you often see written down in papers a sentence like, well, you can consider the constrained form minimize f of x subject to h of x less than or equal to t, or we can consider the penalized form or the Lagrange form, minimize f of x plus lambda times h of x. And here t is the tuning parameter and h is the tuning parameter. And over choices of tuning parameters, these are the same. So we can solve whatever one's most convenient for you. So we're going to actually prove that from the KKT conditions. Or we're going to try to get an understanding of when this is true from the KKT conditions. So we're going to assume that f and h are convex. So let's try to go from the constrained form to the Lagrange form. See what we can do there. Well, if this constrained form problem is strictly feasible, if there's an x for which h of x is strictly less than t, then strong duality is going to hold because it's a convex problem, strictly feasible. By Slater's conditions, strong duality is going to hold. That means there's going to be some lambda, which is bigger than or equal to 0. That's going to be the dual variable corresponding to this this constraint, such that the primal solution is going to minimize the Lagrangian, right, at that lambda. That's just stationarity. So we've just said that if strong duality holds, then the KKT conditions must hold. In particular, the stationarity condition must hold. And that says that the solution to this problem has to minimize the Lagrangian, which means that x minimizes f of x plus lambda times h of x. But look, t here is a constant, right, with respect to the minimization. So we've just said that actually it minimizes f of x plus lambda times h of x, which is exactly this problem. So we said that there is some value of lambda, namely the dual solution. We don't know it ahead of time necessarily, such that the solution in the constrained problem is also the solution in the Lagrange problem. So any solutions of C are solutions of L for some lambda. That's what we just said. Let's go the other way around. Let's go the Lagrange problem to the constrained problem. Well, if x star is a solution in the Lagrange problem, in this one, then let's look at the KKT conditions for the constrained problem. Right, so the constrained problem looked like this. Subject to h of x is less than or equal to t. What are its KKT conditions? Its KKT conditions are that 0 is in the subgradient of f of x plus lambda h of x, a subgradient of h of x. I'm not putting down the minus t there because that goes away when I take the subgradient. And complementary slackness is that lambda is the dual variable here in the KKT conditions. Lambda times h of x minus t has to be equal to 0. And then primal and dual feasibility. So let's suppose that you had a solution to the Lagrange problem form at the parameter lambda. I'm just going to write down the KKT conditions. Try to use lambda and try to use your x, which is the solution, and see if I can satisfy them for this problem. Well, they're satisfied if I take t, which is equal to h of x star. Right? If the solution was x star to the Lagrange problem, if I take t equals h of x star, then, well, complementary slackness is automatically satisfied. This is satisfied at x star because we've assumed that x star minimizes the Lagrange problem. So we've always now formed a solution to the constrained problem. Right? It's kind of obvious in hindsight. The solution is just given by taking the constraint equal to the achieved value of the penalty. It would have been the choice you guessed probably had you not seen the KKT conditions. So what have we shown from the KKT conditions? The conclusion is that solutions of the Lagrange problem form are always solutions of the constrained problem form. So if you solve the Lagrange problem form for any lambda, there's always a t. That means that you've also solved the constrained problem for that value of t. What is that t? It's very easy. Just take whatever the achieved value of the penalty was. On the other hand, we said that solutions of the constrained problem are always solutions of the Lagrange problem as long as the constrained problem was strictly feasible. Because we needed that to have strong duality holes. Okay, so we get nearly a perfect equivalence. The only kind of minor non-equivalence we get is that if we're at the boundary of the parameter t, and we're at a value of t for which this problem isn't strictly feasible, there's only one value of you can only ever make h of x equal to that value of t, not strictly less than that value of t, then there may not be a Lagrange problem form you can write down that reproduces that solution. So it's kind of like at the boundary of this solution path of this problem, it may not correspond to any Lagrange form problem. But besides that, life is good, and you can go flip back and forth between these two problem forms at your convenience. If you don't know the parameter t or lambda, right, then you can just try solving one or the other over a large range of parameter values, and you know that you're really solving the same problem. Okay, the only other thing that I'll say, but I'll just let you go through this in the notes, is that you can check that if the only value of t that leads to a feasible but not strictly feasible constraint set is t equals 0, so that means that, let's suppose that the only time we don't get strict feasibility here is when t is 0, but we still get feasibility. Then we still get an exact, then we get a perfect equivalence between these two problems by taking lambda equals infinity to get the corresponding solution. So that's kind of an informal thing that we often do, is we allow lambda to be infinite to account for the case when we want to make h of x equal to 0. And that, for example, this is what happens when h is a norm. So we get perfect equivalence for norm penalized problems or norm constrained problems. Besides that, we get pretty much an equivalence. So you can go through that logic. I don't have time to go over this because I wanted to get to the last bit on kind of reintroducing the rule of duality. But here's an example of how you can use the KKT conditions to produce a pretty surprising result. And I suggest you look through this if you're curious. The arguments aren't super complicated. They're all on the slides. But I'll just tell you the result, which is that if you have a differentiable and strictly convex function, but you apply that function to x beta, and you penalize according to the one norm of beta. So for example, this could just be least squares, right? F could be, f of, say, u, could be the norm of y minus u squared. That's strictly convex and differentiable. But then we're going to apply it to x times beta. So this is no longer, for example, strictly convex in beta if p is bigger than n. This says that under very general conditions on x, there's still a unique solution in this problem. So it's an interesting result because it's an example where strict convexity is not strictly convex. It's not even close to strictly convex. But we still get uniqueness in the solution. And it's useful for those of you who are interested in, say, sparsely penalized problems. So we get uniqueness under very general conditions. I think there's a question earlier in class as to when is the Lasso solution unique. The answer is pretty much always, and it's on this slide. Okay, I wanted to tie back in duality. So we've seen duality in a couple lectures. We've seen the KKT conditions in this lecture. We still haven't talked about what I think is the most useful aspect of duality, which is that we can often characterize primal solutions from dual solutions and vice versa. And that's what makes the dual construction so useful. I mean, we've hinted at this so far, and we've seen it with SVMs, but to really understand why this is true, we needed to go through duality and the KKT conditions. Now we can really appreciate it. And the logic is very simple. Let's suppose that we have strong duality, right? So we have our favorite convex problem that's strictly feasible. Then we know that KKT conditions are necessary and sufficient for optimality. So if you give me a dual solution that you computed because you constructed the dual problem and you solved it, then any primal solution must satisfy the stationarity condition. Right? If I write down the stationarity condition and I solve for it in terms of x, that is an expression for x in terms of the dual variables. So that's a determination of the primal solution as a function of the dual variables. That's exactly what happened with SVM. Right? We wrote down the stationarity condition. We rearranged it to get an expression for beta. This is a determination of the primal solution beta as a function of the dual solution W. So this is a general principle, right? If we ever solve the dual and we have strong duality, then we can write down the stationarity condition, and that characterizes the primal solution exactly. And we're going to see next time that in many instances, because the dual has complementary structure, the dual is going to be easier to solve than the primal. It could be harder too, right? It just depends on the problem. But in any case, we can always kind of characterize primal solutions in terms of dual solutions. via this relationship. All right. That's about it. I guess I'll see you guys on Wednesday.